Hello everybody, today we're going to be going over our assessment and design results for the Beloit Water Pollution Control Facility project. So the city of Beloit, Wisconsin has a water pollution control facility, or WPCF, that was originally constructed in 1992 and has had several renovations since. Beloit currently has about 110,000 residents and treats about 5.5 million gallons of water per day. However, this population is expected to increase to about 135,000 in the next 20 years, which would add an expected increase of 1.2 million gallons. In addition to this increased demand, it is important that the plant be able to keep up with changing environmental regulations so the city is able to meet the requirements of its discharge permits through the year 2045. For additional renovations, our project will provide an assessment of the existing plant functionality and suggestions for planned improvements to resolve problems, improve efficiency, and ensure capacity for this projected growth. Our designs were built with a total design load of 30 megagallons per day in mind. In total, our renovations and installations are anticipated to cost about $4.4 million. In the following few minutes, we'll be going over these suggested plant improvements in a bit more depth, starting with bar screens, then following along the general flow of the treatment plan onto grit removal, primary treatment, aeration equipment, final clarification, and finally, anaerobic digestion.
Now, we'll talk about the recommended upgrade to the influent screening system and why it's needed for the 2045 design horizon. The Beloit facility currently uses two mechanically cleaned fine bar screens that were originally installed back in 1992 and then rebuilt around 2018. Even though they've operated reliably, they will be approaching the end of their useful life within the next 6 to 10 years. At the same time, the plant's projected flow continues to increase by 2045. The peak hourly flow is expected to reach about 28.3 million gallons per day. That means both existing screens would have to operate essentially at full capacity, around 14 million gallons per day each, just to pass peak flow. When both screens are maxed out like that, there's no buffer for maintenance, temporary outages, or screen blinding. Even a small amount of debris accumulation could create excess head loss or trigger unnecessary bypassing. So from both a hydraulic standpoint and a reliability standpoint, the current setup doesn't provide enough long-term redundancy. For these reasons, the recommended solution is to replace the aging units with two new stainless steel mechanically cleaned fine screens. These would be arranged in the existing two-channel configuration, with the existing manually cleaned bypass screen remaining in place for emergencies. The screens would retain the 6mm spacing, but use a slightly updated bar profile, 5mm bars, with a 6mm gap to maintain strength while providing over 50% open area. Hydraulically, this design keeps approach velocities within the ideal range. At peak flow, the screen would see about 22 cubic feet per second, which corresponds to an approach velocity of roughly 2.4 feet per second in a 3-foot wide, 3-foot deep channel. This velocity is high enough to prevent settling, but low enough to avoid pushing debris through the fine openings. We also modeled the head loss across the upgraded screen, and even at peak flow, the head loss is very small, just on the order of 2 to 3 inches. This is consistent with performance of modern fine screen designs and ensures that we don't create upstream backup issues in the influent piping. Automatic cleaning cycles would continue to activate based on the upstream water level, keeping the screens free of solids and maintaining a stable hydraulic profile. On the screens handling side, the upgraded screens tied directly into the existing wash press system. Based on the projected flows, screening production remains manageable, typically less than a cubic yard per day, even at average design conditions. So the current dumpster haul-off frequency remains appropriate. Overall, this upgrade strengthens reliability, increases hydraulic capacity, and reduces operational risk well into the future. Most importantly, it ensures that Headworks can consistently handle the 2045 design flow without relying on emergency bypass or pushing equipment beyond its intended limits. Replacing the screen now sets the facility up for long-term performance, protects downstream process, and aligns with the recommendations of the facilities plan.
My name is Timothy Zangler, and I redesigned the grit removal system for the Beloit Water Control Facility. The old grit removal system was composed of two vortex-based systems that were installed in 1992 with an accompanying classifier to clean and dry the grit. The vortex system was plagued with mechanical issues, having blades broken off or fallen off that have needed to be replaced. often requiring costly in-house blade manufacturing. They also both have motor noise issues, both emitting rough motor sounds. The classifier has also been releasing odors. The new system I designed contains 3 iterations composed of 2 Grit Kings paired with one Hydro Grit Cleanse system. The Grit Kings remove the grit from the wastewater inflow. The now gritless water continues through the system to primary treatment, and then the dirty, wet grit flows into the Hydro Grit Cleanse to be washed and dried. This new system ups the treatment capacity from 28 million gallons a day to 30 million gallons a day, allowing for higher peak capacity and potential growth in the future. I chose the Grit King system specifically because of the mechanical issues that plagued the old system. Due to the inherent design of the internal chambers of the Grit King, grit is removed at extremely high efficiencies while requiring zero mechanical moving parts or any electrical components. The internal vortex and pressure variations that are created due to the internal construction are what remove the grit from the wastewater. The grit then flows into the Hydro Grit Cleanse classifiers that work similarly to what was previously installed here in Beloit, but are updated and more efficient versions. The Grit Cleanse more effectively cleans the grit and then removes the grit through a dewatering screw, which in turn dries it. What is left is clean and dry grit that is ready to be moved to a nearby landfill. Since there is less water in this grit, it takes up less weight and needs less energy and less money to be transported to the landfill. The Hydro Grit Cleanse system is also a closed system that contains any odor and addresses issues that were present with the old clarifier. Overall, this system is more efficient than what was previously there and really benefits from the Grit King's technology to efficiently remove grit without any need for mechanical parts or any sort of electrical input. This reduces money needed to run this because you don't need any electricity to run this. And also, there will be minimized mechanical failures and erosion on any parts that were there. Previously, different blades and parts used to have to be manufactured, usually in-house at a very high cost, to replace any damage that had happened in the grit removal. But since the internal structure of the Grit King is actually what's responsible for removing the grit, not any mechanical parts, we are seeing a lot more efficiencies and saving money that would previously have gone to any mechanical repairs.
The City of Beloit's wastewater pollution control facility consists of 2 large circular primary clarifiers for the primary treatment process, which follows preliminary screening and grit removal. It is designed to remove settable solids and floating materials before biological treatment at the plant. Wastewater flows and splits into 2 equal and uniform paths before splitting off to the 2 circular primary clarifiers, each with a 100-foot diameter and 12-foot water depth. These clarifiers were originally built and conceived in 1992 when the facility was constructed. Inside each clarifier, mechanical sludge scrapers rotate along the tank bottom, pushing all sludge towards the central hopper. Sludge is continuously removed from the clarifiers using air-operated diaphragm pumps, one in each clarifier. Scum removal is handled by surface skimmers that spin around collecting fog and pushing those towards scum hoppers. From there, scum goes to an inline grinder and is pumped using cavity pumps to a scum concentrator. Scum is then hauled off-site or sent to anaerobic digesters. Since 1992, only one of the round clarifiers has undergone rehabilitation. The other clarifier needs rehabilitation to handle corrosion and equipment malfunctions in some of the pieces. The primary sludge diaphragm pumps were both installed in 1992 and need replacing in both clarifiers. The scum concentrator and scum pumps are also recommended to be replaced and need to be replaced for future projected flows. Overall, the 2 primary clarifiers have been effective since 1992 and will continue to be effective with proper equipment replacement and corrosion and corrosion fixes in both clarifiers.
The aeration system provides the core biological treatment at the Beloit WPCF, supplying oxygen for carbon oxidation and full nitrification. The design uses fine bubble membrane diffusers, which were chosen for their high oxygen transfer efficiency, low energy use, and long-term reliability, a consistent theme across the plant's modernization efforts. Fine bubble diffusers typically provide 8 to 12% SOTE in clean water, which helps meet the plant's biological oxygen demand while minimizing blower horsepower. Based on the calculated oxygen demand of the activated sludge process, the plant requires approximately 6,319 pounds of O2 per day, which translates to an air delivery rate of 454 SCFM. To meet this loading under all operating conditions, the system is equipped with two 25 horsepower centrifugal blowers, each capable of delivering the full design airflow. This ensures Class 1 redundancy, meaning one blower can fully support the aeration process while the other is offline for maintenance. The diffuser grids distribute air uniformly across the two 1.0 mg aeration basins, supporting consistent DO levels, effective mixing, and stable nitrification performance. Overall, the aeration equipment upgrade enhances energy efficiency, improves oxygen transfer, and provides robust operational reliability that aligns with the facility's design goal of meeting 2045 flow and loading conditions.
The final stage of the activated sludge treatment process is final clarification, sometimes also called secondary clarification. This process, much like primary clarification, separates out the remaining biosolids from the treated effluent through settling. In Beloit's wastewater treatment plant, there are 3 circular clarifier tanks that have 125-foot diameters and sidewater depths of about 16 feet. During normal operation, only 2 of them are in use. The tanks are center-fed from a well that receives discharge from the aeration basin and have baffles installed to ensure even flow distribution throughout the tanks. Once the sludge is settled, it will be withdrawn by circular scrapers and directed to a central sludge pocket, after which it will be sent on either to be recycled back to the aeration basin as return-activated sludge or sent for further treatment as waste-activated sludge. This WAS is pumped by 2 centrifugal pumps, while the RAS is pumped by 5, designed to meet the flow capacity of 150% the design average. The performance of the clarifiers was done with the assessment of their detention times, solids loadings rate, overflow rates, and weir loading rates, which were all found to not exceed suggested industry standards. Thus, the capacities of the 3 existing clarifiers were found to be sufficient to meet the 2045 projected flows, so no additional tanks or major overhauls of the existing design were found to be necessary. However, several improvements still need to be made. Historically, the plant has had issues with algae blooms that cause problems downstream, so it is important that launder covers be installed to prevent their growth. The grout at the bottom of the tanks is also well overdue for being replaced. Finally, although RAS and WAS pumps have been rebuilt several years ago, the equipment is aging and replacing them is advised to ensure the performance as flow demand increases. Specifically, on the WAS pumps, the isolated valves require replacement, ideally with electric actuators.
Anaerobic digestion stabilizes sludge, reduces overall solids, and generates biogas that can be used as renewable energy. The system's performance depends on how much sludge is produced and how much volatile material it contains. Design loadings are based on sludge generated from both primary sedimentation and biological treatment. Primary sludge is around 4 to 6% solids, and waste-activated sludge is around 1% solids. The plant is designed to maintain loading in the industry range and achieve 45 to 55% volatile solids reduction. We use mass balance to predict how much volatile material is destroyed, how much stabilized sludge leaves the system, and how much biogas is produced. This information also determines how much heat is required and how much energy is available for recovery. Digester tanks are sized based on hydraulic retention time and based on organic loading limits. Multiple cylindrical tanks are used so maintenance can occur without interrupting treatment. Mixing is essential to keep temperature uniform and prevent settling. Beloit favors mechanical mixing because it is reliable and easy to operate. Biogas is the primary fuel source for heating the digesters, keeping them at around 95 degrees Fahrenheit. Boilers run mostly on digester gas, with supplemental natural gas only during startup, high load conditions, or low gas production. The strategy Beloit should aim for is to maximize resource recovery by using biogas for heating and electricity generation and use flaring gas only when necessary. Doing this will result in the plant reducing energy costs and greenhouse gas emissions while supporting long-term sustainability. Overall, anaerobic digestion helps Beloit manage sludge effectively, recover energy, and improve environmental performance through smart design and efficient operation.
To conclude, our design upgrades position the Beloit Water Pollution Control Facility to reliably meet its projected 2045 hydraulic and treatment demands while improving efficiency, resilience, and long-term operability. Starting at the headworks, we replaced the aging 6mm Parkson screens with two new, mechanically cleaned fine screens, each size to handle half of the future peak load. This ensures full redundancy, reduced head loss, and more reliable removal of debris during high-flow events. Along with this, the new grit system, comprised of 6 Grit King units paired with 3 Hydro Grit Cleanse clarifiers, eliminates the mechanical issues seen in the current Vortex units, reduces power use, and provides clearer, drier grit for disposal. In primary and secondary treatment, the existing clarifiers already meet the hydraulic criteria for 2045 loads, so improvements focus on rehabilitation rather than replacement. These include repairing grout surfaces, installing launder covers to control algae, and upgrading aging RAS and WAS pumps. This extends the lifespan of critical infrastructure while maintaining effluent quality. For biological treatment, our design uses fine bubble diffusers and dual 25 horsepower centrifugal blowers to meet the calculated air demands for roughly 454 standard cubic feet per minute. This setup provides efficient oxygen transfer for both BOD removal and full nitrification, while maintaining redundancy and lower energy consumption. Finally, the anaerobic digestion system is expanded and modernized to maintain the required 15 to 20 day retention time and achieve 45 to 55% volatile solid reduction. Mechanical mixing, improved heating, and effective gas utilization strategies allow the plant to recover energy through digester gas while stabilizing sludge for downstream processing. Overall, these upgrades provide Beloit with a treatment plant that not only meets future capacities, but also improves reliability, operational flexibility, and sustainability. Our design ensures the facility remains compliant, energy efficient, and resilient for decades to come. Thank you for taking the time to listen to our presentation.